So based on the simulation we did on Delta Math, these are the things that you want to have as takeaways. So here is a dot plot, just similar to those dot plots that we made. Okay, now the mean differences here, we see range from negative 1.6 to 1.4. So that's the same idea. You have the two groups, you find the average of each group, and then you find the difference between the two groups. Always group one's mean minus group two's mean. So this data is a little more clustered. We saw like a little bit bigger range on Delta Math. First off, technology is a faster way to randomly assign data values to two groups. So we did a couple by hand where I, entered the mean value, I guess not totally by hand because it was on a computer, but we can quickly generate those dots as we've seen before. This is still the same idea. The computer is randomly splitting the values into two groups, okay? The two group means will tend to differ somewhat just by chance. So this is a chance graph. When we randomly assign them, what happens? The difference in means is always the mean from group one minus the mean from group two, and that way we have some positives and negatives. The distribution of difference values will always be centered at 0. So we have some above and some below just by chance. When there are a large number of difference values, this is the same as what we saw with those proportions. The shape of the distribution of the difference values will be symmetrical and approximately normal. Therefore, difference values that are closer to 0 are more likely to happen by chance. So we kind of expect those ones closer to 0. Difference values further from 0, outside on the normal curve, are less likely to happen by chance. I use this word, and this is a word we're going to be using, when a difference value is statistically significant, which means a real difference, probably not just a chance difference. It means that we are 95% sure, so there's our number again, that the difference value is a real difference that did not just happen by chance. So here's where it gets a little tricky. When we were doing confidence intervals, we were always taking the middle 95%. So we go something like this. Okay. Now I can't, and maybe I'll go this way a little bit more. I can't really, it's kind of hard on the regents to tell which one they want. Usually it's something in the wording. When we do these statistically significant differences with a difference in means, we also sometimes just look at one side, okay? And we did have this in a recent Delta Math assignment where they said to look on one side. So if I'm on the top side, how many dots are to the right? If I'm on the bottom side, how many dots are to the left? So we call this value a p-value. So a p-value is the probability of getting a difference value in this re-randomization graph, the graph that's up at the top of the page, that is the same or more extreme than the difference value from the experiment. So that's where we're going to the side. We're just looking at one side based on that value. To determine if the difference value from the randomized experiment is statistically significant, find the p-value, and we will be doing this. If p is less than 0.05, then the experimental difference value is statistically significant because it would occur less than 5% of the time by chance. So we only look on one side. It's not 2.5 on each. We are at least 95% sure that it is a real difference, something that rarely happens by chance. So this process is similar to the 95% confidence interval, but we are putting all 5% of the unusual values in one of the tails instead of splitting it up and giving 2.5% for each tail. If the problem says to use a 95% confidence interval, use the middle. Okay. Otherwise, as I said, you'll see some clues about being on one side in the problem. P-values are typically included in reports and experiments because it shows exactly how unlikely it is that the difference value from the experiment occurred by chance. So you'll often see something like P equals 0.01. Okay. That's pretty statistically significant because it's much lower than 0.05. This gives more information than just saying a result was statistically significant or not. It gives us like how unlikely it was to happen by chance. So I'm going to make this smaller. I'm going to read the question first. Identify the p-values for the difference values of negative 0.8. So we'll do negative 0.8 first. And 1.2. Nope, not 1.12, 1.2. in the dot plot above, which has 100 difference values, and that is important. So looking at our dot plot above, when I'm at negative 0.8, we are saying how many values are at negative 0.8 or more extreme. So I'm basically, the negative 0.8 is on the left side, so I'm going to count up these dots. If I counted up those dots, there are 20 of them. There's 100 total dots, so we would say P equals 20 over 100, or 0.2. So that means that 20% of the time we can expect to get a number that's negative 0.8 or smaller, okay? Not really statistically significant. We're not answering that question on this page, but 20% is not really small enough. Now for the 1.2, that's in the other tail. So 1.2 is here. There's only 4 dots that are more extreme. So if I do for the negative 1.2, the p-value equals 4 out of 100, that's 0.04. So since that's smaller than 5%, it happens, 1.2 does happen by chance, but not very often. So we consider that statistically significant. If we did an experiment that was set up with this difference value chart, we would say that's statistically significant. So on this page, we're going to do the same thing, but take it one step further. So we are going to find what is the probability of obtaining a difference value of negative 0.6 or less. And I kind of wish I went in the other direction for this, but it's okay. We're just starting out. So here's negative 0.6. So we can already see probably not statistically significant. So the P is, and actually, so there's 9 in this row. So the last one we had, this is the same graph as the last page. We had 20, so this is 29 out of 100. So P equals 0.29. So do you think a mean difference of negative 0.6 or less would be considered a statistically significant difference? No. And we can simply say P is greater than 0.05, right? That's our cutoff. What's the probability of obtaining a mean difference of 1.4 or more? So there's 1.4 or more. So that's P equals 2 over 100, which is 0.02. And so would a mean difference of 1.4 be considered statistically significant difference? Sorry, trouble saying that. The answer would be yes, and that is because P is less than 0.05. Okay, so there's less than a 5% chance of obtaining a 1.4 by random chance.